In the last video, we modified the work energy theorem so the work by conservative forces was reclassified as the change in the potential energy of the system, or actually it became the negative of the change in the potential energy of the system. And then the work energy theorem equation became the conservation of energy equation, which looked like this, which says that the change in the kinetic energy of the system plus the change in the potential energy of the system, which is associated with all of the conservative forces, and we only know of two so far, the gravitational force and the spring or elastic force. And that equals the work done by all of the non-conservative forces on the system. The conservation of energy is a fundamental and powerful concept in physics. In this video, we'll discuss it in a little more detail and then learn how to apply it. First, there are different ways to write the conservation of energy equation. The way I've written it here basically expresses the concept that the total mechanical energy of the system, represented by the left side of the equation, will only change if work is done to the system, or in other words, if energy is added to or removed from the system. Mathematically, we can expand the deltas in the kinetic and potential energy terms so that the equation becomes this, and then putting the final energies on the left side of the equation and the initial energies on the right side of the equation, it looks like this, which is another common way to write the conservation of energy equation. Written like this, it expresses that the total final mechanical energy of the system here equals the total initial mechanical energy of the system here, plus the total work done to the system. In many applications, the system is isolated so that no work is done to the system. When this is the case, the equation simplifies to this, or we can combine the kinetic and potential energy terms and just indicate that the total final energy of the system equals the total initial energy of the system. Again, these last two equations are only true when there is no work done to the system. Keep in mind that all of the equations written here are really the same equation. They're just algebraically organized in different ways. Regardless of how the conservation of energy equation is written, we should always recognize the fundamental concept that the total mechanical energy of a system won't change if work is not done to the system. Now let's discuss applying the equation. As we've done with our previous major principles, we'll start with a procedure. This is essentially the same equation that we used with the work energy theorem because the conservation of energy equation is just an expansion of the work energy equation. The only thing I've done differently in this procedure is to add coordinate schemes here for the potential energy terms. We've only discussed the gravitational potential energy so far. We'll discuss the spring or elastic potential energy in the next video. Let's practice the conservation of energy procedure by going through a basic example. A skier is near the top of a hill with an initial speed of 4 meters per second. As the skier goes down the hill, what is her speed when she has dropped by a vertical height of 2 meters? Neglect friction and air resistance. The first step in the procedure is to draw a diagram. So here's the skier in the initial location with an initial speed of 4 meters per second. And then in the final location going at the unknown final speed that we want to find. As indicated in the procedure, we should also include a y-coordinate axis, which will be used when calculating the gravitational potential energy. Next, according to the procedure, we should show the forces acting on the system, or in this case on the skier. These forces are the normal force, the gravitational force, the drag or air resistance force, and the kinetic friction force. We're told to neglect friction and air resistance, but I'll leave them in the diagram this time for discussion purposes. Showing all of the forces acting on the system will become very useful when we begin to apply the conservation of energy equation. So let's do that now. Here's the conservation of energy equation. I've used the original form of the equation, but the other forms we discussed may also be used. Let's first look at the work term on the right side of the equation. This is the net work by all of the non-conservative forces acting on the system. This is where the force diagram becomes useful. There are 4 forces acting on the skier, 3 of these forces are non-conservative forces, so there should be 3 work terms, one for each of the non-conservative forces. One for the normal force, one for the air resistance force, and one for the friction force. You should make sure that all of the non-conservative forces acting on the system are accounted for by the work terms on the right side of the equation here. The 4th force acting on the skier is the gravitational force. This is a conservative force, so it is accounted for in the potential energy term on the left side of the equation here. Every term in the conservation of energy equation is associated with a force, except for the kinetic energy term, which is associated with speed. One thing that the force diagram does is to help ensure that all of the required terms are included. So now let's deal with each work term, starting with the work by the normal force. Let's apply the equation for work, force times distance times the cosine of theta, where theta is the angle between the force and the displacement vectors. For the normal force, theta is 90 degrees, and the cosine of 90 degrees is 0, so the work by the normal force is therefore 0. There's also work being done by the air resistance and friction forces. In both cases, theta is 180 degrees, and the cosine of 180 degrees is -1. So the work by each of these work terms is negative. For this particular problem, however, we're told to neglect these forces, so these work terms are also 0. On the left side of the equation, let's expand the delta terms into final minus initial terms, and then replace each kinetic energy term with 1/2 mv squared and each gravitational potential energy term with mgy, so the equation becomes this. We can then clean this up some by dividing out the mass in each term and recognizing that per the coordinate scheme, y final is 0. And now we can solve the equation for the final speed, and then plugging in values, we find that the final speed of the skier is 7.4 meters per second. As a final comment, I want to point out that some problems can be solved with either kinematics or the conservation of energy. However, there are some problems that can be solved with kinematics and not the conservation of energy, while there are other problems that can be solved with the conservation of energy but not kinematics. As an example, consider the scenario of dropping a ball. If air resistance is neglected, we can calculate the speed of the ball after it has dropped 1 meter with either kinematics or the conservation of energy. For practice, you might try solving that problem with both methods. I'll give you a hint. If you solve it with the conservation of energy, it's mathematically identical to the problem we just did, so you should ultimately get this equation again. If the ball is dropped from rest, the initial speed is 0, but the rest is the same. On the other hand, if we want to know how long it takes for the ball to drop 1 meter, then we must actually use kinematics, because the conservation of energy equation does not include the time variable, so there's no way to solve for the time. How about the skier problem we just worked through? Could we have solved this problem with kinematics? The answer is no. Recall that the kinematic equations are only valid when the acceleration of the object is constant. In this problem, the slope of the hill changes, so the acceleration of the skier is not constant, and so we can't use the kinematic equations. So that's it for this video. Thanks for listening.